Hello, and welcome to the Group 5 Interim presentation. We'll start with an overview of the system goals and setup. Our objective is to design an integrated energy management system to minimize the payoff period of a solar and battery subsystem installation based on appliance electricity savings. Inside the system, we include factors related to the solar panel and battery designs and home energy usage patterns. Outside the system, we've excluded factors such as seasonal and extreme weather, as they are unpredictable. We aim to solve the system-level design problem to address the growing environmental and economic need to convert to more renewable forms of energy. An optimization model will be useful to appropriately balance the needs for inexpensive setups with maximum utility savings. Shown here is our system flow diagram. The solar optimization uses average weather conditions to output usable AC power to the battery and system costs to the payback period. The battery optimization uses the AC power from the solar subsystem, grid charging, and the appliance load demand profiles to output available discharge energy to the appliances and system costs to the payback period. Finally, the appliance optimization uses the available battery energy, the grid power supply, user interface requirements, and home electrical infrastructure to output a daily appliance load profile to the battery and an electrical cost savings to the payback period. The subsystems are repeated here in a textual format. Our solar subsystem will handle energy generation, our battery subsystem will handle energy storage, and our appliance subsystem will address energy usage. To recap our linked variables, there is a two-way interaction between subsystems 2 and 3, with available battery energy being sent to the appliances and energy usage needs being sent back to the battery. This ensures that the battery is not over or under designed. Between subsystems 1 and 2, we have a one-way relationship with usable generated power being sent to the battery.
Our first subsystem is energy generation, which will be achieved through the use of solar panels. In the solar generation subsystem, the inputs is the solar irradiance, with weather conditions factored in, and the outputs are the usable power and the value of said produced power. We define key design variables shown here with the respective units. Our intermediate variables have to do with the position of the sun relative to the panel. These allow us to then calculate the power generation, energy output, and money saved. The system is subject to important constraints, including the physical roof size and shape, a maximum supported mass of 2,000 kilograms, and a total budget limit of $20,000 for reference. The overall impact of this work is a more efficient use of roof space, increased electricity generation, and improved financial returns from solar installation. On this slide, we present the mathematical model and optimization approach. The power generated by a panel is modeled after P equals area times efficiency times solar irradiance times the tilt factor, which accounts for the roof angle relative to the sun. We solve this as a mixed integer linear programming problem using MATLAB's interlink prog function. The goal is to select the best combination of panels that maximizes electricity value while satisfying cost and mass constraints. To determine placement, we first define the roof as a polygon, then scan it row by row to evaluate available space. Based on the available width, we place the optimal combination of panel sizes. The final output is a set of feasible panel placement locations. The entire process was implemented in MATLAB using the optimization toolbox with solar data sourced from the National Solar Radiation Database.
The model determined that the optimal solution is 47 panels, producing about 140 kilowatt hours per day, which gives an estimated daily savings of $21.39. We also ran the optimization 5 different times using different day indices, and everyone returned the exact same results. Both the mass and cost constraints are active, meaning the solution fully utilizes the available budget and roof capacity. The consistency occurs because the problem is linear and deterministic, and integer programming guarantees a global optimum. Now briefly on the code, this function takes a panel placement and combines them with solar radiance data and time-based electricity pricing. It calculates energy generation for each panel, converts it to that value, and then uses MATLAB's interlink prog solver to determine which panels should be installed while satisfying the constraints.
Now we move on to subsystem 2, energy storage through the use of a battery. Our goal through subsystem 2 is to maximize battery lifespan while minimizing total lifestyle cost. To do this, we focus on 3 key design variables: battery capacity, depth of charge, and discharge rate. These directly control how much energy we can store, how aggressively use the battery, and how well we can meet peak demand. The system takes in solar generation and household load as inputs, and tracks internal states like battery energy level and charge and discharge power. We also impose realistic constraints, including limits on depth of discharge, total capacity, budget, and physical space. Overall, this subsystem acts as the bridge between solar generation and appliance usage, improving reliability, reducing grid dependence, and extending battery life. For the battery optimization, we use a linear programming model to determine optimal energy storage. The model runs hourly, capturing how energy flows between solar, battery, and the grid throughout the day. Key inputs include solar generation profiles, household demand, and time of use electricity pricing, along with hardware cost assumptions. The outputs give us both optimal battery size like energy capacity and discharge power, and operational decisions such as when to charge, discharge, or when to pull from the grid. This allows us to enforce real-world constraints while ensuring the system minimizes grid reliance and overall energy costs.
Energy storage results. We evaluated 5 scenarios by varying key constraints like budget, space, pricing, and load to understand system sensitivity. A key takeaway is that both energy and power matter. A large battery is not useful if it can't deliver enough power during peak demands. We also see that the system performance is strongly constrained by real-world limits like budget and space, which can prevent the optimal design from being fully realized. The system is most sensitive to electricity prices, which drives both battery sizing and cost savings. Finally, the baseline scenario, run 1, is the most robust, providing a balanced solution across all constraints. Overall, this highlights a trade-off between performance, cost, and practical limitations in battery system design, leading us to optimization results of a 15.4 kilowatt-hour battery.
Our final section of this presentation will discuss the optimization process and results for home appliance energy usage. The main objective of our model is to maximize daily electricity cost savings. We will achieve this by manipulating the load start time, mode selection, and power source by choosing from either the battery or the grid. The subsystem parameters relate to grid costs, battery storage, appliance power consumption and duration, and set usage frequencies. Our model is subject to constraint by user requirements, which prevent the units from starting outside of an acceptable window. This constraint works in the model's favor, as the acceptable start times ultimately occur in moments when grid costs are high and while battery power is increasing. The model is also constrained by a minimum expected utility value, which was imposed to indicate user preference for heavier duty cycle performance. We may also be limited in our power draw based on the home breaker limits, which could prevent the appliances from being used simultaneously in the best cost window.
An analytical model was chosen for its speed and simplicity since each appliance can be defined using discrete variables. We use a genetic algorithm to efficiently explore a wide range of scheduling combinations, especially for this kind of discrete and nonlinear problem. We evaluate costs under 2 scenarios, one with a battery system and one without, and use the difference to estimate realistic cost savings. So this slide shows the optimization result across different scenarios and how changes in constraints or parameters affect the cost savings. For round 2, even though the grid price goes up, the optimized solution doesn't really change. That's because the higher price mainly affects the case without the battery, where you'd already shift the schedule to reduce grid usage, so the overall savings stay pretty similar. For round 3, we assume the battery is not available. In that case, everything runs on the grid, so both scenarios end up the same, and there's no cost savings. And for round 4, we tighten the time window for when appliances can run. The schedule doesn't change much, but savings actually go up, since using the grid becomes more expensive within the limited time. Thank you for listening. Please feel free to reach out if you have any questions or feedback.